Mechanics 2020 new problem, roller coaster problem. This is number 3. All right, so we have from A to B is a concave down parabola, and then from B around to D we have a quarter circle, which is the first part of a semicircle track. And then we have a roller coaster here that is not going to leave the track as it goes down from rest. All right, what's the direction of the acceleration at points A and D? Now we have two different points here. We're going to have two different accelerations. So at point A, our acceleration is going to be tangent to the circle. And down to the right. If you just let go from rest, this guy will accelerate down the track. It will accelerate along the track, not into the track, not off the track. And at point D, now it's moving with a velocity. It's moving sideways, but it's not accelerating down anymore, and it's not accelerating up anymore. Tangent to the track, I mean. It's accelerating off the track into a circle. So it is perpendicular to track into circle. And we typically call this centripetal. Oh yes, and up. And that looks like 1 over up, doesn't it? I mean that to be, it is perpendicular to the track into the circle, which we're also calling up. All right, part B. The force is acting on the coaster at point C. So at point C, they have chosen that on purpose, because at point B, the track is essentially falling out from underneath it. You would only have gravity. You don't have much from the track there. That's the transition between the parabola and the circle. But here, we're definitely in the circle. So if we draw a free body diagram at point C, we're going to have the weight downwards, and then perpendicular to the circle, we're going to have the normal force from the track. Now what about friction? They very kindly turned off friction and air resistance for us. So we're going to say weight points straight down, and normal force from track is perpendicular to the track. That is what normal means, but you need to spell it out for these people. Pointing up and to the right. All right, C. I'm gonna have to get rid of these guys as I scroll down. All right, part C. We have an equation here, 6t squared minus 0.4t cubed. And then we have a graph for the distance. Explain how the graph could correctly model the motion of the car during the first 5 seconds. Okay, so at the beginning, we're told that it starts from rest. And if you take a look here, a tangent line to the distance function is horizontal. So point number 1 is graph and equation both start with slope equal to 0, consistent with the situation that car starts at rest. All right, and point number 2 is slope of the graph and derivative of equation both increase from 0 to 5 indicating that the speed is increasing. You need to have both of these written into your answer for part C because they are both relevant in part C. Now in part D, instead of looking at the first half of the graph in the equation, now we're going to look at the deficiency in the second half. The second half is how are we not modeling it correctly for this part. All right, there are again two aspects relating to the speed at a particular point as well as what's going on there. So, whoops, I left that on erase. D. All right, so number one, slope should continue to increase from 5 to 10 as speed, get an S there, speed of car will increase from B to D. It's still, here, let me scroll back up. The car is still going down from B to D. It's still going from having potential energy to having kinetic energy, so the velocity is still going to be increasing more. And the graph should reflect that. The graph instead is concave down, indicating the slope of the graph is decreasing, which means the speed is decreasing, and that's not how a kart would behave on that track. All right, and the second thing is slope at time equal to 10 should be steepest because car will be fastest at D. Graph shows that the car would have zero velocity. At 10 seconds, which is also known as point D. Now, what we can see here is we have a situation, and then we have a model of that situation, and that model looks pretty good for part of it, but then for the other part, it's not so good. We're going to have to adjust our model. You have to keep in mind that we're not changing the track to fit the model. We're going to change the model to fit the track. So when we come down to point E and F, or parts E and F, we're going to talk about a new model here. I'm going to have to close out this guy and reopen it. That'll be the fastest way to clear that guy out. All right, now parts E and F. We have the correct model. They don't tell us what that is. They just say, hey, we found the right equation now. Now, how are we going to determine the height difference from A to D now that we have the correct model? So now we have x of t equals something. So, well, if we have x of t equals something, that means that we can take the derivative and get v of t. Okay, that'll help us, especially at 10 seconds. So take the derivative and then find v of 10. Now, they also told us there's no friction. This is very helpful because then we can use conservation of energy using PE at point A being transformed into kinetic energy at point D. Solve for height using above equations. Now at part F, we're at point D, and the track is exerting a force on the car. So let's go back to, I'll draw a diagram here. So we have this guy, and then we have our cart on there. And since it's moving in a circle, the acceleration is upwards into the circle. But you have to keep in mind, it still has weight out of the circle. So when we're looking at the force from the track on the car, we're going to have to account for both the fact that it has weight and it's accelerating upwards into the circle. Now, if you said that it has no acceleration at point D, you're going to be ignoring the fact that it's accelerating into the circle, and that's going to mess up most of your answer for part F, because it depends on the fact that it's accelerating into a circle. So for part F, we have the normal force equals minus weight equals mv squared over r. And what we want to do is find this guy. So how are we going to have to find that guy? Well, we're going to have to add the weight to the other side. You need to make sure that you mention that. And we're going to have to find the radius, and we're going to have to find the velocity. So how are we going to do that? 1, obtain velocity using equation and method mentioned in part D. 2, we have to get the radius. We're not told the radius. What we are told, let me scroll back up to look at the track. What we're told is the distance from B to D is 100 meters. And we're also told, so where are we told that? Where did I come up with that? Oh, here we go. The distance from point B to point D is also 100 meters. Okay, so we're told the distance, that's the arc length from B to D. And we're also told that from B to D is a quarter circle. Are we told that directly? No. The track then smoothly transitions to a half circle between points B and D, with D as the lowest point on the half circle. So they're telling us indirectly that from B to D is a quarter circle. So we need to get the radius of that circle. And we're told that's a quarter circle. We're also told that this arc length is 100 meters. So this guy's 100 meters. So we need to get radius using arc length of 100 meters that's given, and the quarter circle from B to D, which is going to be pi over 2. So we're going to get the radius using that, we're going to get the velocity using that, and then the last step is going to use centripetal, use Newton's second law with centripetal motion and add weight of car. So this is where I would use this equation to indicate that. Fn equals mg plus mv squared divided by r. And you can do this because you've already mentioned you're going to get velocity, and you've already told them how you're going to get the radius, and now you're saying I need to add the weight. You're using this equation to clarify how you're doing 1, 2, and 3 and how it all fits together. But this equation is not replacing your verbal explanation for how you're going about solving the problem, which is the main point of how these questions are written for this year.